yesterday. And so I guess I'll just recall a bit of our setup. So remember, our goal right now is we have X is a KLT threefold. F is a rank 1 foliation. Or maybe not goal, I should say setup here. And we have a flipping contraction. So a flipping. Is a flipping contraction. So recall that this just means that minus KF is eta ample, and the exceptional locus of eta is one-dimensional. So there's just the flipping setup. And of course, the problem is that we have a foliation. So we have F, we have a foliation, a push-forward foliation on Z. But the problem is that the canonical class of this foliation is no longer Q Cartier, so we can't continue the MMP from Z. So we have to do, as Pyle was explaining, we have to perform a flip surgery. So the idea we had, or the idea for producing the flip surgery, so the KF flip, what we want to do is first find, so we had two problems. We wanted to find many F invariant divisors SI containing C, and then two, bound the singularities of X some SI, or maybe some perturbation of this, which I'll explain in a bit. And then what we realize is that if we solve these two problems, what we see is that the KF flip will be a KX plus some SI flip, which is known to exist by BCHM. So we know that these log flips exist. Okay, so yesterday we I guess Pyle explained how we solve one, how we do one. So yesterday we I guess we finished step one. And the idea, so just to recall, the main idea was to use a foliated version of complements. So recall that the key step in this was we found, so there existed an effective divisor, an effective V divisor, in fact, D. So Z V divisor, such that KF plus delta was linear equivalent, Q linear equivalent over Z to 0. And so this implies that, well, as I said, and as was pointed out by someone's question yesterday, eta star, the push forward foliation, is not Q Cartier, but this log canonical divisor is Q Cartier. So I guess this condition right here implies that this thing is Q Cartier. And so then this is log canonical. And then the trick is you just sort of use standard results about normal forms of log canonical vector fields to produce. So maybe I'll say we can use we can use, I guess, some standard results. So normal forms of log canonical vector fields. To produce the SI. Okay. So maybe before going on to explain how we do two. So this is just a summary of what we did yesterday, or part of what we did yesterday. So before I go on to explain two, I maybe want to give a concrete example of a flip. So normally it's a bad idea to give concrete examples of flips because in practice, we don't really know what they look like. We just know that they exist, but what an actual flip looks like is a bit mysterious. And this is just one of the strange things about MMP. But a nice thing about, especially in rank 1, we can actually give some very concrete examples, some very simple concrete examples of some foliation flips. So I want to give an example so we can kind of, fix ideas about what's happening, and then I'll come and we'll sort of see exactly where what the SIs are in this case, and then we'll come back and it'll kind of indicate to us the right way to bound the singularities of this pair. Okay, so let's consider X is P1 cross P2 fibered over P2. Okay. And let's let F just be the foliation, so I'll call this pi. F is the foliation induced by pi. So it's just a P1 bundle by pi. And let's fix a point X in P2. And let's let C be the preimage of X. So C is just a P1. And let's pick a point. Let's pick a point on this P1. I'll call it P, and let X tilde just be the blowup at P of X. And we can still take F tilde to be the transform foliation. Okay, so just to be super concrete, what we have is we have a P2, we have P1 bundle, and then we're going to blow up a single point. So we're going to we have a P2. Okay, so there's one thing we have to check is what's the actual foliation? What are the leaves of the foliation? So this is sort of an important point. This P2 is of course not a leaf because it's two-dimensional. Rather, we get induced rank 1 foliation on the P1, and the induced rank 1 foliation on the P1 is just the maybe I'll use a different color, is just the pencil of lines passing through the point. And what you can check is that the normal bundle, so if we let C tilde be the strict transform of C, you can just check the normal bundle of C tilde inside X is just O of -1 plus O of -1, so we're gonna do that right. And we can flip it. And what's happening in the flip? The flip is going to look like we blow up C2 and then blow it back down in the vertical direction. So what's going to happen is, so we'll call this E plus, and maybe I want to use a different color for C also. And now C plus is transverse to the foliation. So we take a curve, we take C plus or C tilde plus, and we flop it and we get a curve which is transverse to the foliation. And this foliation now, this is the foliation induced by this is an actual fibration to P2 blown up at the point X. So this is, so Now, it's a bit of a red herring. You could forget about the bottom half of this picture, that it's fibered over P2 or P2 but the point is that the local picture is always, or the picture upstairs is always the same. And this is an example of a foliation flip. As we'll see, at least for rank 1 foliations on 3 folds, essentially every foliation flip looks like this. Okay, so what's happening? So where are we getting our SIs from? The SIs that we're constructing are basically just the pullbacks of all these divisors, bunches and bunches of divisors on the P2. And as Pal explained, that there's no way a priori to control, if you have a bunch of divisors invariant by a rank 1 foliation, there's absolutely no way to control the singularities of that pair. So maybe I should want to remark. So, yeah.
On the left, the CT that is invariant.
Yes, yeah. It becomes non-invariant. Yeah, yeah. So I want to, yeah, maybe, yeah. This is, yeah. So a remark. C tilde is invariant. C tilde plus is not invariant. Yeah. It's strange, exactly. Yeah, but so I guess, okay, yeah, maybe it looks a bit disturbing. The reason why it's maybe not so disturbing is, I mean, think about what's happening, think about what's happening on E. E is the foliation given by a pencil of lines. And so I mean, it's if we just forget about the threefold foliation for a second, what's happening is that the flop or the flip is resolving this foliation singularity. And the resolution of this foliation singularity, because it's log canonical, extracts a divisor transverse to the foliation. So yeah, one important feature is that what we'll see, or as I'll explain out in a bit after we construct the flip, every flip, there's going to be, for every flipping curve, there's going to be an invariant surface transverse to it, such that the restricted foliation has a log canonical surface, a log canonical foliation singularity on it. And the non-invariant divisor hiding over that bad singularity is exactly the C plus we extract. So that's another way of viewing what the flip is doing. The flip is resolving some log canonical foliation on this invariant divisor transverse to the flipping curve. So yeah, I think this is nice because this is a very concrete example, and yeah.
No, is like F1.
Yeah, it's exactly, it's F1. Yeah, exactly.
Every time you have a flip, you have a singularity.
Yes, yeah. So maybe I want to emphasize this too. Yeah. Yeah. So maybe I'll even prove. Yeah, that's a good point. I should prove this for you guys. It's not hard. As I say, it's not surprising, but it's an important thing to remark. And I think maybe we mentioned it before, but just to because it bears repeating. In any case, is so observation. If C is a flipping curve, then C cap or C intersection with sing F is always, in fact, it's always just a single point. It's always just one point. So maybe what I'll do is I'll prove that it's non-empty, and then maybe you can sort of believe why it has to be a single point when I explain why it's non-empty. So the proof is just Reeb stability. So let's just suppose X is smooth. In general, X won't be smooth. So we need somehow a version of Reeb stability for singular varieties, but this isn't such a bad thing. This isn't too hard. Let's suppose X is smooth. Now, Reeb stability says that if you have a foliation, L is a compact leaf with trivial fundamental group, but really finite's enough. So if you have a compact leaf with trivial fundamental group, then every leaf near L is isomorphic to L, or is homeomorphic to L, maybe I'll say. And so what we see is that suppose that C was disjoint thing F. Well, we know by what Powell was telling us yesterday, C is a rational curve. In fact, it has to be a smooth rational curve. In particular, P1 of C is trivial. Reeb stability then implies that every nearby leaf of the foliation is again P1. So actually in a neighborhood of C, the foliation is given by a P1 bundle. And so C has to move. So that all nearby leaves are P1. And so C moves. But this is a contradiction, right? Because by assumption, a flipping curve is something which can be contracted, and contractible curves can't move. I mean, this is Growler's theorem. So by Growler, I mean flipping curves are rigid. So yeah, so it's essentially a consequence of Reeb stability that that every curve has to meet, every flipping curve has to meet the singular locus. And I guess I'll sort of just leave it as an exercise maybe that it has one such intersection. Okay. Cool. You don't seem happy, Fabio.
Sorry, I was thinking of the following thing. So if you take maybe this is something stupid on the schema, take a foliation in P2, highly genus.
Yeah.
And take this smooth point and blow it up. And you have a P1 which is invariant.
Definitely. But it's not a compact leaf. Because if you blow it up.
Because that's what I meant. Because leaf, you mean that there are no singularities around.
There are no singularities on it. Yeah.
Okay.
So yeah. Yeah. Again. Yeah. So at the very exactly. Yeah. That's why I want to be kind of fastidious about. Exactly. Yeah. So that's why I was trying to be fastidious back on Monday about my leaves are always disjoint from singularities. So we can actually state things like this. Otherwise, we could say a compact invariant divisor disjoint from the singular locus if we prefer. Yeah. So yeah. So I guess I want to recall. Leaves intersect singularities is always empty for me. Yeah. Okay, great. Thank you. Okay, so this is, so this is. No, so I claim, that's, it's equal to exactly 1 point. So okay, so maybe, so maybe I'll explain why it's exactly 1 point, because I mean, you're right. I mean, that's an important point, and I guess I shouldn't cheat you guys out of that. So thanks for asking. So the observation is, okay, so this goes back to a junction. So okay, let's just again suppose that X is smooth. Okay, when X is singular, again, you have to be more careful, but it's not a big deal. So what we knew from a junction is that Kf dot with C is going to be equal to Kc plus some different. We got some different delta C. And where does this different come from? Well, we have our Pfaff field, which by invariance restricts, we get some commutative diagram like this. And so this is where a junction comes from. So delta C, so maybe if this is our fat field C, maybe I'll call it phi sub C. So phi C is supported exactly where phi sub C drops rank. Because it's just given by where this map fails to be surjective. And everything in sight is a line bundle. But the point is that this map drops rank exactly on the singular locus of the foliation. So this is equal to sing F intersection with C. And so we see now that now if C is P1, we see that delta C is an integral divisor, and the degree of delta C has to be strictly less than 2, which implies the degree of C of delta C is exactly 1. And so we actually get that we have exactly one singular point. So. Well, our singulars are log canonical. I mean, it's usual flipping setup. So Carolina's question was, so I just said that C intersected with the singular locus of F was non-empty. So I guess I should say, Reb stability implies that C intersected with the singular locus is non-empty. And then Carolina's question was, well, why couldn't it be a bunch of points? Why is it exactly 1 point? Yes, so that's a consequence of the cone theorem. So I guess I should say, okay, I'll give you a cheating answer and then I'll give you a real answer. So so the fake answer is that the cone theorem implies that I guess the cone theorem for rank 1 foliations. This is I guess I want to emphasize that this is a very special feature about rank 1 foliation. So maybe I want to really emphasize this. So rank 1. Cone theorem implies that if C spans an extremal ray, then C is not contained in the singular locus of the foliation. Okay, now why is that? Well, yeah, exactly, extremal, yeah, but make that Alex. So why? It actually turns out something a lot stronger is true. It turns out that if F has canonical, so if the rank of F is 1, rank of F is 1, F has canonical singularities, then F restricted, or then KF restricted to sing F is semi-ample. In particular, Nef. And this is actually a pretty direct argument by Michael McQuillan, Bogomolov and McQuillan. So this is their observation. So for rank 1 foliations with canonical singularities, actually you know a lot about what's happening. Maybe I should be on the normalization of the singular locus just to be safe. Okay, so that's just for rank 1. So, but I want to, I mean, we haven't talked so much about higher co-rank foliations, but this is something very special about rank 1 foliations.
Sorry, a question about stability, but
yes.
what do you apply? I mean, is here in a leaf or?
So in this, so what we're supposing is, so C is our flipping curve.
Yeah.
So we know that C, did I erase it? C looks something like this. It's some curve generically tangent to the foliation.
Yes.
Maybe it has some singularities. it's irreducible. So it's an irreducible one-dimensional subset. So it is at its generic point, it's a leaf. So it's not a union of multiple leaves. But now we're supposing, for sake of contradiction, that it's actually disjoint from the singular locus of the foliation. In which case, yeah. So this is for our absurd hypothesis, yeah. And so now it really is a leaf in this absurd universe. But yeah.
Why do you get this semi-equivalence? You see nothing like this for the canonical divisor.
No, exactly, yeah. Because for the canonical divisor, the singular locus of the trivial foliation, the foliation with one leaf is always empty.
So why do you get it? So is there any idea why you get this?
I mean, okay, I'll have to. I can give you a good answer. I mean, it's actually a very simple argument. I mean, the point is that you just if you know. I mean, so the idea is it's just some linear algebra basically. Is you look at this map, and then you look at the differential from I. Let's see here, from I. And you have a non-zero map like this. And the idea is just by analyzing this map, you can produce lots and lots of sections of KF restricted to the singular locus. That's the point. But I don't know. You could do the calculation. I'm not sure how illuminating it is. And so if there's like an intuitive geometric reason why this is happening, I don't have an answer because yeah, there's nothing like this in the classical case for the foliation with one leaf. So yeah, this is maybe I want to. This is a very strange thing that happens. I guess I want to draw everyone's attention to this. This is a very strange thing. And in particular, I guess what I want to say is that it's not true for rank 2 foliations. So in rank 2, this isn't true. So I guess I'll say there exist flipping curves contained in the singular locus. So, and it's not hard to produce these examples. Maybe if we're interested, I can, there's a whole zoo of examples that I have, and that one has, and then we can parade them out if we're interested. But just so this is only true for rank 1. Okay, so I think this concludes the proof, a very long proof of why every flipping curve meets the singular locus in one point. So I guess we've had a bit of a walk down the garden path here, but okay. So okay, cool. So now it's totally erased. It's gone forever. But so what we've done is we've said something about what flipping curves look like, and now what we have is we're on step 2 of Paolo's plan. And so what we have is we have these invariant divisors SI containing C. And what we want to do is we want to somehow bound singularities. Okay, so a priori, there's no way we can control the singularities. So we have to do something about this. Okay, so we're going to do this in a sort of a 2-step process, and I'm going to present it this way because this is going to introduce an important threshold. So I guess so. For people not coming from a birational geometry background, thresholds show up a lot, and different kinds of thresholds show up. So I'm going to introduce log canonical thresholds. And these are some important invariants. So this is completely besides foliations, whatever. We're forgetting about foliations for the moment. So let's let X be a log canonical variety, or yeah, I mean, I'll just say it like this: a log canonical variety. There's of course a more general setup. So in particular, KX is Q Cartier, and D is an effective Q-Cartier divisor. And we define the log canonical threshold, LCT, of X and D to just be the supremum of all T such that X comma TD is log canonical. And we're assuming X is log canonical, so we know that this log canonical threshold is well defined. So it's not, minus infinity or something like this. Okay. So what I want to do is I want to look at the log canonical threshold in a neighborhood of the generic point of C. So as examples show, so all our examples where, these examples that Paolo produced yesterday of cases where this has bad singularities, they're basically all constructed in the same way. You have a foliation which comes from a map down to a surface, and then you pull back some very crazy singularity or some very, very singular divisor from the surface back along the projection of the foliation, and you produce this pair with very bad singularities. So what I want to say is let lambda be the log canonical threshold, or let's say let U be a neighborhood of the generic point of C, and let's let lambda be the log canonical threshold of U with respect to the sum of the SIs. So what we're doing is instead of looking at the log canonical threshold along all of C, which might not be a good idea, we're just looking at it in a neighborhood of the generic point of C, and this is what we're calling lambda. And so what we see then is that the pair X lambda sum of the SI is log canonical except at finitely many points. Wait, which one? U. X is KLT. Remember?
The variety scale.
Yeah. That's a part of our flipping setup.
And is that preserved as your own?
Yeah, so something even better actually. Yeah, so maybe I'll say this again in a bit, but yeah, it's one of the miracles is actually the rank 1 foliation preserves quotient singularities even. So if you start off with a variety of quotient singularities and you run the rank 1 foliated MMP, you preserve quotient singularities. So KLT gets preserved. But yeah, so this is something you have to do. It's something that maybe I won't have time to explain, but it falls out of a lot of the stuff that actually the singularities of the underlying variety are preserved as well. Yeah, good question. Thanks.
The effect of the quotient you cannot prove with them, like my code.
Yeah, well, no, actually, no, that's not true. It's it actually follows from the negativity lemma. Yeah, so the way Michael constructs the flip. Okay, so the Michael flap, I guess is what the proper term for it is he explicitly constructs a weighted blow up followed by a explicit weighted blow down. And so you know that if you're doing just a sequence of weighted blow ups and weighted blow downs, you're going to stay in this, the quotient singularity category. Of course, what Paolo and I do is we do some MMP flip. So a priori, you have no control over the singularities that show up. There could just be random KLT singularities. But the neat thing is that somehow you know very precisely what terminal foliation singularities look like. So I didn't mention the word terminal at any point. It's I guess because Paolo, we defined canonical, log canonical, and KLT, but not terminal. So terminal is another class of singularities. But so for those in the know, the point is that if you do a flip, actually your foliation has terminal singularities at closed points along in the neighborhood of the flipping curve, and that's enough to guarantee that you have quotient singularities. But you see, this is just a consequence of the negativity lemma. So actually, it's very and classification of terminal singularities, which isn't so bad. Exactly. Yeah. Exactly. That's what it is. Terminal plus Gorenstein is smooth. Yeah. Yeah. So it's actually, yeah, it's just abstract nonsense. I mean, insofar as the negativity lemma is abstract nonsense, but bless you. Okay. Yeah. So oh man. Okay. Oh, so yeah. Okay. So yeah, so the problem, the thing now is we have these finitely many. So we have this divisor, which has nice singularities, except perhaps at some finitely many points. Maybe there's a few bad singularities. So I guess the way to fix this is something that Pal and I do. And it's I'm sure there's probably a more general statement than this floating about, but I don't quite know what it is. So I think that's a good problem, is figure out where this fits into a broader framework. So let's let X be a normal variety. And let's let D be, and I guess F, a rank 1 foliation with canonical singularities. And I guess I want to emphasize that this is the rank 1 case here. And D is an F invariant divisor such that X minus P, D minus P is log canonical, where P in X is just some closed point. Then XD is log canonical. So you get this sort of propagation of log canonicity type theorem. So maybe I want to sketch a quick proof.
Another quick question, but there you took U instead of just all X because you wanted the curve to be a log canonical standard.
Exactly. Yeah. Exactly. Yeah. So this. Yeah. The reason for doing this is I want C to be an LC center, and so exactly. Okay. So the proof of this is actually kind of simple. So what we can assume is you can reduce to the case to KF being Cartier. So F is generated by a vector field. And then what I want to look at is I want to take a DLT modification, which is equivariant with respect to the action of this vector field. So, I'll say what I mean by DLT modification. The reason why I'm introducing this proof is I think this tool of a DLT modification is a very powerful tool, and I think more people need to know, the world needs to know about it because it's a pretty useful idea. So a DLT modification, which is equivariant with respect to the action of our vector field. So vector fields correspond to local group actions. And so all we're saying is that this DLT modification is equivariant with respect to this local group action. Or maybe put another way, you can realize this FDLT modification by blowing up in F invariant centers. So what do I mean by a DLT modification? So by a DLT modification, it's just it has the following properties. So let's let E just be the exceptional locus of of our morphism. I guess I'm calling it pi. D bar is the strict transform of D plus E. X bar, D bar is log canonical. In fact, it's DLT. Whatever that means isn't so important, but it's some natural class of singularities. But X bar, D bar is log canonical. KX bar plus D bar is pi nef. And if we write X bar plus D bar, we can write plus D where F is greater than or equal to 0. So this is all a DLT modification is. It's some modification which satisfies this list of properties. The idea is that it's worse than a log resolution of the foliation because this is some partial resolution which might not make X bar D bar smooth, but it has additional important geometric properties. So you have this extra nefness of the transform, which you don't generally have for an arbitrary resolution. So these two properties are somehow these are the nice things, the good things about DLT modifications. But you can't achieve them just doing log resolutions. Okay. So we take this DLT modification. And because it's F equivariant, or because pi is delta equivariant, there exists this lift delta tilde, a holomorphic lift to X bar, maybe I'll call it. Now, let's let S be a component, a divisor in the exceptional locus. And what you can check is that we have, by adjunction, we can write K of F restricted to S as, well, okay, maybe here's what I want to claim. I want to claim that if we write KX bar plus D bar restricted to S bar or S, we write this as KX bar or KS plus BS, then KS plus BS is not big. And the proof of this is pretty simple, actually. The idea is that delta bar restricted to S leaves BS invariant. So actually what we have is we have a global section of H0 TS minus log BS. But varieties of general type don't have any infinitesimal automorphisms. So KS plus BS cannot be big. So BS has infinitesimal automorphisms. So KS plus BS is not big. Okay. And so then the point is you go to the log canonical model. So let X bar can, D bar can be the ample model of X bar D bar over X. Now, what we know is two things. X bar can, D bar can is log canonical by assumption, or because it's the ample model of the log canonical pair. And two, well, this contraction, we know that every single divisor in the exceptional locus has to be contracted by passing the ample model, because none of the KX restricted to any ample divisor is not big. And so so if, I guess if we let, I don't know, call it C from X bar can, we see that the push forward of E is 0. And so X bar can to X is a small modification. But you have a small modification of a pair, which is log canonical, and therefore original pair was log canonical. So this implies that XD is LC. Okay. So this is a very technical thing. But again, the basic observation is that you use this vector field and this, I guess this is equivariant resolution to control what the sort of divisors you're extracting in a DLT modification. And so you see that the ample mod of any DLT modification has to be a small modification. Okay, so this was exactly what we needed then. I mean, it's small, and it's small, and kx plus d is q Cartier. I mean, if it's not Crepin, yeah, the divisors have nowhere to hide. It's yeah. Okay, so what this tells us then is that this pair we constructed. So erase this. So X lambda SI is log canonical. And this is exactly what we needed. And this was step 2 of what Paolo was describing. And so this is step 2 is finished. And so now what we realize is, and just to emphasize, the KF flip ends up being is a KX plus lambda SI log flip. And that shows that flips exist. Okay, so so I have 10 minutes left. So I guess initially, okay, so this explains the proof of existence of flips and modulo termination, and therefore existence of minimal models for foliations on 3 folds. Maybe one thing, one thing I guess I should say, maybe just out loud, is that we, and Paolo mentioned this too, is that we have the existence of minimal models for foliations with algebraic leaves. So I guess,
Is it obvious that the curve is negative for that very construct?
Yeah. Well, obvious, no, but true, yes.
Okay.
Yeah.
I don't want to go any further.
Yeah. I mean, I was debating. I mean, because I think I don't know, Paolo, if you're planning on explaining why it ends up being. I mean, it's an adjunction statement. Yeah. I mean, adjunction. But yeah. Otherwise, yeah. So I guess. So one thing I want to. Oh,
maybe I'll comment. Then in this, the adjunction is important. I mean, the fact that C is a log canonical center comes into place here.
Exactly. Yeah. So we're going to use some souped up version of Calum subadjunction,
Okay.
And the existence of this vector field controls the moduli part of that shows up in Calum subadjunction. So okay. So maybe what I want to do is, okay, so yeah, like Paolo said, we can do all this stuff for algebraically integrable foliations. I mean, modulo some recent work we're working on. So flips exist for algebraically integrable foliations. This, I think, is an important thing. I mean, as we somehow, in all the examples of flips we have on 3-fold, somehow there's always an algebraically or there exists like some form of meromorphic first integral for the foliation whenever we have a flip. And this seems to be a general phenomenon about flips, that somehow the dynamics of the foliation around flips are always very simple. And so somehow we expect that once you know that flips exist for algebraically integral rank 1 foliations, this somehow contains a lot of the hard work for proving that flips exist in all dimensions. Just because somehow the dynamics of foliations in your flipping curves can't get too complicated in some sense. So this is kind of hand wavy. so even if all you care about is transcendental foliations, somehow even knowing the MMP for algebraic integral foliations is still, you know, something of interest. Maybe what I want to end on though are some things that I don't know, and things that I think would be really great if people would try and answer. Okay, yeah. So the first one is log canonical flips. Somehow throughout this whole story, we've used the canonicity hypothesis a lot. Somehow what we do doesn't work for log canonical flips. And it's not exactly straightforward to reduce log canonical flips to canonical flips. So this is a big mystery to me, or what one has to do. I think this is a good question. Yeah, so I should say, yeah, I mean, yeah, so there's a bigger class of singularities, FDLT, but I guess the point is FDLT singularities are always non-dicritical. So I guess the challenge is dicritical flips. This seems to be the trickier one. I don't quite see how one would do it. But yeah, so I think this is a really good question. Another one is flops. This I think is much harder. I think this is a very hard problem understanding flops for foliations. I believe this is some work with Palo. So with Palo, we think we can do co-rank 1 flops in dimension 3, but rank 1 flops, I don't think anyone has any idea about how to do them. So this is, yeah, this seems to be really hard. I guess I think this is a really hard problem, but maybe I'm wrong. Okay. Maybe another question, which I think is pretty interesting. So in the proof of flips, we use the existence of these things called complements. And so Carolina and Stefan Druel have this really nice sequence of papers on phonopholiations. So I guess I encourage everyone, you know, to check out their. Sorry, I guess the first paper is on phonopholiations, but I guess this. And of course, there's a lot of nice papers following it. And so I encourage everyone to check these out. And then the question I want to ask is, do complements exist for phonopholiations? So somehow Paolo and I proved a local version of this statement. And somehow I expect understanding this question to be important for flips in higher dimensions. And the fourth one, maybe just I'm running out of time, I guess, is a Sarkisov program for foliations. So maybe to give some context for this, when you run the MMP, so outputs of the MMP are not unique. This is an important feature or an important aspect of the MMP. We have to make choices when we run the MMP. So it's not really an algorithm, right? But at every step of the MMP, we're choosing an extreme array to contract. And so as a result, there's a non-uniqueness which creeps in to the whole story. And so the question is, how are two different outputs related? And okay, and so the Sarkisov program, at least in the case where we have a Mori fiber space, in the Mori fiber space case, it should tell us some sort of answer to this question. Okay, so maybe I'll end there unless Paolo has anything he wants to add. But yeah, I guess. Oh,
I mean, if you want to mention the fact that for rank one.
Oh, yeah, I guess I should say, yeah. Except in rank one. Yeah, that's another strange thing about the rank one MMP is, yeah, the MMP is essentially unique, which is very, very odd. No, you can flop fibers, yeah. So I guess, yeah, yeah. So if KF is Ceph, then yeah, I guess, yeah. So okay, I guess I'm hiding. This is so the Sarksoft program is for the KF not Ceph case. When KF is Ceph, we expect that minimal models are connected by sequences of flops. So I guess the point is that for rank one, you don't need flops. Two minimal models where KF is Neff are automatically isomorphic. Cool. Well, I guess yeah, maybe I'll end there. Thank you.
Any questions?
The last question is like the minimal models. I mean, conjecturally, of course, they should be connected by flops.
Yeah.
And in rank one, they're all isomorphic, means that there are no flops.
There are no flops. Yeah, no flops are needed. Yeah, they're isomorphic.
The flop is not isomorphic.
Exactly. Yeah. You take a variety. You run two MMPs. You actually get the same thing at the output. Even if you run a priori, maybe you contract things in different orders, but you don't have a case where I mean, the outputs are exactly that.
Questions?
Cool.
Well,
let's yeah. Thank you.
And we'll resume in 1 hour.